Thanks very much, Noel. Thanks very much for the invitation to come back here. It's really nice to visit and see some old faces here again. So, as Noel said, I work in the area of computational biomechanics, and in the talk today, I'm going to just cover, I guess, a background to bioresorbable materials and look mainly at two of the main categories of biomaterials that are biodegradable. So metal-based biodegradables and also polymer-based biodegradables in, I guess, a range of both orthopedic and vascular applications. So in terms of my research group in general, as Noel said, my PhD was in the area of composite micromechanics. So I've kind of kept that theme running through my current research, looking at computational biomechanics across a range of different length scales. So we do a lot to understand, I guess, cell, tissue and organ level behavior in the areas of bone fragility in particular. And I guess in between the tissue and organ scale, we work a lot in the area of medical devices. So to try and understand, I guess, the role of biomaterials and the design of medical devices and applying computational methods to better understand and better design medical devices for implant applications. So in terms of medical implant development, I guess the development of medical implants currently is almost completely founded on experimental testing. So this is a typical workflow where you have a new product design, it goes through a wide range of, I guess, in vitro bench testing, then it will move on to preclinical animal testing and eventually moves on to clinical trials and human studies. And I guess a real problem with this type of approach is that if you have an unacceptable outcome at any of these stages, you move right back to the start. Okay, so what you don't want is to fail out here when a device is implanted in a human or is in kind of the post-market phase. And for us and the work in my group, what we try to do is to, I guess, inform designs at an earlier stage. So to use computational methods so that you can essentially fail early and get better informed designs before you go to anything like animal trials or clinical trials. So in the area of bioresorbables, we work in both orthopedic and vascular bioresorbable implants. I'm going to look at orthopedic implants first. So in the area of orthopedics, the removal of fixed metallic implants is the most common elective procedure carried out in the EU. So it's about 5% of all orthopedic surgeries. So if you have a bone fracture and you have a fixation plate applied to that fracture to aid healing, once the fracture is healed, that plate is typically removed. Okay, so that requires a second surgery that creates complications in terms of, an additional surgical procedure. You can have problems with infections, and getting the implant actually out of there, when I'm talking about a permanent metallic implant, is a messy procedure. So in the field of bioresorbables, I guess the idea is that you have an implant that goes in here and gradually degrades with the natural healing process of the tissue. So this is a typical kind of a time scale for what you want in terms of mechanical stability of a fracture region. So initially you have low bone stability due to the fracture region, and your implant, which is bioresorbable, has high stability. As the implant gradually degrades, your bone stability increases during the healing process, and the two kind of work in concert with one another such that the overall stability of the region is maintained. Okay, but in terms of designing bioresorbable implants, you have distinct challenges because the implant must, I guess, behave, to perform, quite a hard load-bearing function at the start of this process. Then in the immediate term, it must, degrade in a way that matches the natural healing process of the tissue, and then in the later stages, it has to be completely removed by the body without causing any adverse reactions. So the two main categories of bioresorbable materials are either polymer-based or metal-based. And typically, when I talk about metals, they tend to be magnesium alloys. With both of these materials, they have advantages and disadvantages. So with polymers, what they have is very controllable degradation, so they can kind of they don't degrade too quickly. However, their mechanical properties tend to be quite low. For magnesium alloys, these have higher mechanical properties, so obviously because they're metal-based, but they tend to have uncontrollable degradation processes. So with both of these, it's finding a balance between being able to fulfill, load-bearing functions, but also being able to do that for sufficient time such that the fracture region is adequately supported. And in terms of bioresorbable materials, there's been several famous cases where bioresorbable implants have failed in the post-market surveillance area. So there's an ACL screw from Smith and Nephew that failed after it was clinically approved, and also the Abbott Absorb device, which is a vascular device, failed from poor late-stage clinical data that happened 2 years post implantation. So both of these happened in around 2016, 2017, and this essentially kind of pushed the field of bioresorbables back quite a bit in terms of a lot of confidence was lost in bioresorbable implants, particularly in the vascular space, where kind of more traditional permanent metallic implants became more widely used or were maintained. So one of the projects that I'm involved in and that I coordinate is what's called the Biomplant ITN program. So this is a multidisciplinary and multi-partner program where we're looking to develop next generation bioresorbable materials for vascular and orthopedic applications. So this is a multi-partner project where NUIG are partnered with several other international partners in Europe. I'm going to talk first about a lot of the work that we do in the area of magnesium bioresorbables, and this work is done in partnership with Miotech, which are a small startup company in Germany who produce magnesium-based materials for a range of different applications, with a particular focus on the biomedical space and the implant space. So looking at metal-based bioresorbables first. So in terms of metal-based bioresorbables, typically they use magnesium-based alloys. Magnesium AZ31 or magnesium WE43 are commonly used alloys for medical implant applications. And I guess the advantages with this material in terms of kind of obviously it's metallic, so you can apply a lot of the same processes in terms of production that traditional stainless steel cobalt chromium implants are produced by. It also has other advantages, so it has similar properties to the native tissue. So it has a Young's modulus between about 40 and 50 gigapascals. Obviously, it absorbs over time, so the second surgery becomes redundant, and it's also osteoinductive, so it actually promotes bone growth when you implant it in an orthopedic application. But it tends to degrade rapidly, and this is one of the disadvantages of magnesium. So magnesium, if it's, I guess, unprotected, can degrade in the body in about 6 weeks, which is, pretty much before any healing process would be completed. Another disadvantage is that corrosion takes place in a highly localized manner. So it undergoes what's called pitting corrosion, and therefore you can get early failure of an implant due to kind of localized attack of the material. So in terms of that, I guess your process by which the implant degrades is corrosion. So it's a surface-based mechanism where material is removed from that surface and it gradually breaks down. In terms of pitting corrosion, it results in non-uniform removal of the surface material. So this is an image adapted from a book on surface corrosion, where you get these distinct pits forming on the surface of the structure. And obviously this is a localized attack, so that can lead to, I guess, a non-uniform decrease in property. So this is an example of surface pitting corrosion in a bridge truss frame, where you can see these distinct localizations of pitting corrosion, which obviously as a structural engineer is going to cause significant stress concentrations and put that structure under stress. And this is also seen in magnesium implants. So here, this is your specimen strength versus percent mass loss. And even with relatively small levels of mass loss, you can get a drastic reduction in specimen strength in a magnesium structure. So in terms of understanding that process and understanding how surface corrosion links to mechanical properties, we have some guidance from standards. So there is an ASTM standard that can, I guess, gives guidance on actually quantifying features of pitting corrosion, but it's quite qualitative. So they have a number of metrics where you can look at pit density, pit size, pit depth. They tend to be kind of visual quantification metrics to give an idea of how corroded a particular surface is. They also have some other parameters that are defined within that standard, which one of these is pitting factor. So this is the maximum pitting depth over the average pitting depth. So to try and get an understanding of, I guess the deviation in pits. So if this was your maximum pitting depth here, your max over your average pitting depth might be somewhere here. So this structure might have a pitting factor of maybe 2 or 3. But I guess despite the definition of these standards, there's actually very little link, or there's no relationship really that has been established between pitting corrosion and mechanical performance. So that's the work that we have been looking at over the last 3 or 4 years in this project that we've been carrying out with Miotect. So I'll run through some of our experimental mechanics tests first. So what we've been doing is looking at corrosion performance of WE43 dog bone specimens. So these are our tensile specimens that are produced by Miotect, our company in Germany. And we essentially immerse these in a corrosive medium for 28 days. And we evaluate, I guess, the evolution of surface corrosion and also evaluate the mechanical strength of these specimens. So to look at corrosion of these samples, we came up with an approach which uses micro CT scanning and a kind of a spatial quantification of corrosion on the surface. And we related those parameters to mechanical strength by doing uniaxial tensile testing. So I'll go through these in a little bit of detail. So in terms of our immersion testing, so these are our 3 dog bones here, and this is the actual corrosion that takes place in the gauge section of these dog bones. So this guy here would have been after 28 days, and you can see like a highly non-uniform attack of that structure compared to what your initial nice dog bone would have been. In terms of an initial measurement of corrosion, we use evolution of hydrogen gas. So as your magnesium corrodes, you get hydrogen gas given off, and we measure that in the corrosion test, and that gives us a measure essentially of percent mass loss of that structure. So this is your evolution of hydrogen gas over the 28-day period here between 7, 14, 21, and 28 days. So, and traditionally, I guess, that is how corrosion would be measured in an experiment. So you might do an experiment on a new magnesium alloy that was developed, and people will put it in an immersive media. They'll measure hydrogen evolution and they'll say, okay, it has this amount of mass loss over this time period, and they probably won't look at mechanical data or really try and understand the actual features of those corroded samples. So that's really what we were trying to address with this. So to look at the corrosion of that surface, what we had is we had a micro CT based approach. So we took these tensile specimens, we micro CT'd them in a micro CT scanner, and we essentially created a binarized image of these samples. And from that, we developed an automated framework that could, measure the surface features and I guess fully recreate your 3D geometric section of that. So in terms of the inputs from this, so this is what you get when you carry out a micro CT scan of a metallic specimen. So obviously with a metallic specimen under micro CT, it's highly dense, so you get a very I guess a high or intense image. but you can see that you can differentiate here the degradation layer or the corrosion layer that forms on the surface. So this is your magnesium core, and this is your corrosion layer on the surface. And through a series of reconstructions, we can actually recreate the core region here without that corrosion layer. From that, we process this image. So here you're looking at one single 2D section of that gauge section, and we apply essentially an automated detection framework to essentially get a series of measurements from an outer circle fit to the core region here. And from this interpretation here, what we identify is essentially a series of pits around this surface. And this is carried out in 3D, so it takes into account the layer above it as well. And this is essentially what we characterize as a pit around that material. And once we have the pit defined, so we have pit depth, we have pit volume, we have how they vary in space, we can come up with a series of parameters that defines those pits. Okay, so what we have plotted here on the bottom is the output from this. So this is our gauge section rolled out in a 2D plane. So this is kind of, if you imagine this being, you know, the revolved surface of that gauge section, and you can see how your pits actually develop on that surface, where by 28 days you have these large pits that are kind of occurring and that are coalescing from, say, the early phases. So the contour here is pit depth. So that's the depth of the pits that are being created on the surface. From that as well, we can, you know, do a histogram. So look at the probability density of pit depth on these different surfaces. So after 7 days, you have a lot of very small pits. So you get a distribution like this. As you move to 28 days, these small pits have grown and possibly grown into another. So you get a wider distribution here at your 28-day time point. So we also have some other parameters that we'll relate to later when I go through our mechanical properties. But obviously, because these are in, you know, they're nice uniaxial dog bone specimens, we can mechanically test these. And this is the uniaxial test data from the dog's bones that were tested. So the black line here is the day 0 specimen. So you have a specimen strength of just around 260 MPa, and you have, you know, good plastic behavior, so quite a ductile material. As you start to get pitting, you start to get a reduction in specimen strength, and you also get a reduction in strain to failure of the material. So plotted here, we have our UTS, or maybe our specimen strength over our mass loss. So here you start to get a drop off or a reduction in specimen strength as you start to lose mass. And this dotted line here is, I guess, the theoretical strength if you had uniform corrosion. Okay, so if you didn't have any stress concentration and you just had a uniform reduction in cross-sectional area, you know, this is how it should behave. But with localized and pitting corrosion, you get a much more rapid drop-off. And what we were able to do with that then is, because we have the geometric data and because we have the mechanical data, we can start to relate spatial data to mechanical properties. So what we looked at first was some of the ASTM standards. So we looked at plotting specimen strength versus the various pit density, pit size, and pit depth parameters. And let me just focus in on some of these. What we found was, when you plotted specimen strength against pitting factor, you found a very poor correlation in terms of mechanical properties. So that idea of looking at the max pitting depth versus the average pitting depth didn't really tell us much mechanically about the specimen. One of the other metrics is looking at the average pit depth of the 10 deepest pits in a particular specimen. That starts to give a better correlation. So It's maybe about some of the deepest pits that are responsible for your drop off in mechanical properties, but still not a perfect correlation. So we started looking at some other metrics that we were able to define based on the geometric information that we have. So let's just highlight a few of these. And we started to see very good correlations when you start to look at, I guess, metrics or parameters that are directly related to the radius or the minimum width of that specimen. So things like average radius loss, or even the standard deviation of radius loss from the specimen. So, you know, averaged over this average over this 2D section, but, you know, at the lowest point along the 3D stack, started to give very good correlations in terms of UTS. And then looking at the minimum core width, so the minimum distance that was tracked across the entire section is highly correlated with UTS. And that makes a lot of sense as an engineer, because your specimen is only as strong as its weakest cross section. And I guess with that, a lot of that makes sense, you know, when you kind of do the data and what the data turns out to. But I guess what it suggests is that if you're designing an implant, your minimum feature size is really, really important. So if you have an attack on, you know, a region of the implant that has a narrow section, that could be very detrimental to that implant. What we then wanted to do was to, I guess, look at developing some models around this. Okay, so we looked at developing a finite element based corrosion model to, I guess, predict surface corrosion in these implants. And there's been several types of corrosion models proposed. So you can have physically based models that will, you know, kind of capture the chemistry or the physics that takes place, but they tend to be very localized models. They can't be, you know, widely adapted to larger structures. Another approach is use a phenomenological approach, so using continuum damage mechanics or an element removal method to remove elements from the surface. And from some of the early models that were developed, one of these was by James Grogan, who was in NUIG about 10 years ago working with Peter McHugh. These were good and could capture, say, certain features in terms of how mechanical strength might degrade over time, but still had issues in terms of the corrosion profiles that we produced tended to be V-shaped, so they tended to be quite simple, and they didn't really, you know, capture kind of the true features that you see in terms of what was happening in corrosion of real samples. And they also tended to be heavily mesh sensitive. So if you change your mesh for these structures, you can get a different corrosion profile. So we looked at, I guess, improving this this model with a PhD student of mine. So here we took the same approach. So we use a continuum damage mechanics approach to, I guess, implement, I guess, damage in these surface elements. So I'm sure people who are working in computational mechanics are very familiar with the idea of degrading degrading the elastic modulus of an element to increase the effective stress. And within our kind of definition of what a surface-based model is, we have what's called a damage increment that describes the corrosion kinetics. So here we have a damage increment, so an increase in damage in the definition of the element based on a term Ku, which is essentially a corrosion rate, and a length term, which is a characteristic size term based on the size of that element. And for uniform corrosion, it's kind of simply defined by these two terms. And to implement non-uniform corrosion, we introduce an additional term here to essentially prescribe a random distribution to the entire material volume. So every element here is prescribed a value that is essentially a probability of corrosion taking place, and that probability can be controlled by a simple Weibull distribution. So depending on the Weibull that you apply, you can change your overall kind of type of corrosion that progresses. when you prescribe a probability function, across your elements, you don't have a continuous probability. So one element can have a low probability and its neighbor could have a high probability. So we go through a smoothing step just to create, I guess, somewhat of a continuous distribution of probabilities across the element volume. And our overall damage increment then is described by this term. So here we have our normalized term here, where we prescribe, I guess, that propensity to damage over the entire range of elements in that material volume. Our L active term then is the characteristic element length. Previously, models used to just estimate this based on a cubic element. So you would see this LE term here, which is just a characteristic length based on the cubed root of the volume of the element. But we found that gave problems. So our implementation essentially works out the actual element geometry and works out the characteristic length based on the direction of corrosion in that particular direction. Okay, so this is its implementation. So it's implemented in Abacus, but we also implement it in Python. And it happens as a pre-processing step to any finite element. So you conduct your corrosion to get a new geometry, and then you can apply whatever loads you want to that geometry. Okay, so this is our comparison then between our enhanced corrosion model and, say, the original model. So here, this is a random distribution that's prescribed to this 2D cross-section, and what you see is you get, I guess, a better description of the types of pits that are formed, and you get kind of multi-directional pitting, you get large pits forming, you get small pits forming. So kind of gives a more realistic representation compared to this this model here. And you can also model uniform corrosion. So here, this is, a kind of a more random distribution, whereas this is a much more uniform distribution provided so that you can actually predict anything from highly random to highly uniform to give you, whatever type of corrosion that you want to predict on your specimen. We kind of did a verification just to show essentially that our model is mesh sensitive. So in terms of what we've plotted here, this is your mass loss over normalized time. Again, the original model has a sensitivity to the number of elements. So if you prescribe a different number of elements in the original model, you get a different corrosion rate. It was just a feature of the model, whereas our one has kind of normalized all those effects, so you get the same rate of corrosion with different element sizes, which helps you when you need to mesh large structures. Okay, so we went through that process for a number of different parameters, depending on what parameters you pick for your Weibull. Our corrosion model would predict the same rate of mass loss, which is important when you start to compare or start to design implants. Okay, and again, just looking at, I guess, the types of features that are produced. So, even just by regenerating your random seeds, you get kind of different features being produced that we could kind of correlate back, at least qualitatively, to what we had seen here in the different features of corrosion. You could also change, I guess, those features based on your input parameters. So here, this gives you kind of a more aggressive pit formation, whereas when you start to increase this gamma value, you get more uniform corrosion taking place on that surface there. And we also have a term which is called the pit radius that can essentially describe or define the size of pits that actually tend to form. So here you can kind of get a lot of small pits, whereas if you increase that pit radius, you get much larger pits forming. So let's take a look then of computational versus experimental. So now we had a model, I guess, to capture corrosion that was taking place, and we had data generated from our first study, which was only based on 12 dog bone specimens. So what we wanted to do was really to apply this out and start generating more scenarios from our computational model to kind of build up, you know, a picture of different types of corrosion and try to understand the mechanics of this. So what we were able to do is take the corroding finite element specimens. So these are the same kind of gauge specimens that we had from FE, and we could just binarize these images and put them through our same automated detection framework to get all the characteristic features of corrosion in that space. So here you see your pit depth based on the finite element models that are being produced here. Again, we could see kind of similar features that when corrosion started, you get quite a narrow distribution as you have a small number of pits. That gradually moves into a wider distribution as your pits grow and start to coalesce. And then we plotted our spatial features versus mass loss. So what we have plotted here is we have our experimental values in red dots, and then we have a series of different corrosion scenarios plotted as the line plots. And what we found is that for several of our metrics that we looked at, so things like minimum width, cross-sectional area loss, average radius loss, volume of all pits, our experimental values tended to overlap with these scenarios. So they tended to recreate what had happened in the experiments. And the one exception to this was our pits per centimeter squared. And that was just due to, I guess, a limitation in mesh size. But a lot of the other spatial features were actually being reproduced by the computational model. And what that, I guess, allowed us to do was to, you know, use that model then as a way to extend the parameter space of, you know, what we could look at mechanically. Okay, so here we model the same dog bone specimens and applied tension to them. We calibrated an elastic plastic law based on the day zero data. So this matched our day zero experimental data, and we applied a range of different corrosion scenarios to these gauge sections and did a tensile test, so a simulated uniaxial tensile test to generate more data around this. Okay, and there's a lot of data here, but again, this is our day zero data, and as we kind of simulate corrosion through a range of different scenarios, you get the same behavior where you get a loss in specimen strength and you get a reduction in strain to failure predicted by the model as well. And again, these are our predicted mechanical strengths, our Young's modulus, overlapping with the experimental data, kind of capturing or being seen to capture what's going on. And I guess we extended this again and looked at the same parameters. So we looked at a lot of these different pitting parameters in the experimental study, and here these red dots are repeated here, but now we've added to this data set essentially through the computational simulations. And again, we found like anything related to the specimen radius started lining up and giving really good correlations with specimen strength in terms of kind of dictating what was happening in those scenarios. And again, that kind of, you know, tells you that in terms of designing, again, your minimum feature size is really important, and just generally controlling mass loss. And I guess in particular, let me just go back, you know, say with even just a small reduction in mass loss. So if you get a mass loss here of 10%, you get a drop off in mechanical properties substantially. So anything that can delay that initial mass loss will extend the time frame of your magnesium specimen that's implanted. So that becomes very important. And if we move on just to some applications, as I said, we worked with Myotech, who are a company in Germany, on a lot of this work. And they have essentially been developing technology to enhance corrosion resistance of magnesium alloys. So one of their kind of USPs is, firstly, they have a very high purity magnesium alloy that, I guess, with fewer impurities in the alloy, they have better corrosion behavior because of that. But they also have a PEO coating, which is an oxidation process that essentially converts the surface of your magnesium to a kind of a hydroxyapatite or a ceramic-based coating to protect it from corrosion. So this is some data from Kirsten, our PhD student, where you see the uncoated specimen here in the black line and the coated specimen here in red. So you get about a 3-fold decrease in the corrosion rate to improve overall corrosion behavior. This company is also looking at additive manufacturing. So they have an in-house laser powder bed fusion system where they generate different patient-specific scaffolds and implants. And one of the areas that we're working on at the moment is just looking at comparison between additive manufactured and extruded magnesium plates. So you do get a slight difference in terms of your corrosion rates for additive manufacturing, but it's something that they're looking to continue to improve with their coating technologies. Within this bioimplant project as well, I guess there's some other nice work taking place where some of our partners are looking at developing magnesium PLA-based composites. So I guess I mentioned at the beginning that you have magnesium, which corrodes very quickly, and you have polymers which have a much better control of degradation behavior. So combining this as a composite, which I'm sure many people here will be familiar with, you can create a magnesium reinforced polymer composite. So these are your magnesium fibers reinforced within a PLA matrix, which is also biodegradable, and you can look at kind of classical tensile and data like that to produce a new material. What they're actually finding is when you combine these, you get a lot of decohesion at your fiber matrix interface here because of the corrosion layer that's being formed. So these materials haven't worked all that well, but if there's a way to control your corrosion at that fiber interface, you could have a structure that would have a significantly longer life than just a traditional magnesium wire. And as well, we work with RWTH-ACN on textile-based structures. So we've done a lot of work with, I guess, braided structures for polymer stents, and we've worked with braided PLLA, which is a polymer-based system, but also we've worked with braided nitinol and magnesium structures as well. So this is kind of some of their manufacturing capability that we've done a lot of modeling around. Just come to the end of, I guess, of our magnesium section. So I'll wrap up and not go into the vascular devices because I think you had enough there. Yeah, I'll come back. So yeah, happy to take any questions from anybody. So.
Okay, so excellent talk, really interesting stuff there. So what we'll do is we'll take questions from anyone watching remotely. If you want to type, if there's anyone who has a question, they could type or talk. If you're talking, put on your camera. Just see if there's anyone there, or raise your hand or indicate. Oh, I see some hands raised there. Armand, with the people clapping, sorry.
Turn them up.
Okay, that's fine. So for people in the room then, if there are any questions, Ted, you can probably handle your own questions there.
I'll go first?
Yeah, sure.
Sure, Ted, yeah, cheers for that, very interesting. The corrosion experiment that you did, the timescale of that seemed, and maybe I'm completely wrong, but seemed aggressive compared to if it was implanted in the body and how long it would degrade. So how does that affect what you're doing?
So I guess within the work that was done there, what you want is, I guess, something that's controllable and repeatable. Typically, a corrosion experiment like that would have maybe an accelerated time frame of about 4-fold. But but it depends on the corrosion setup that you get. So corrosion in vivo will be much slower. So that took place over 1 month. That might relate to about 3 to 4 months in the body. And I guess we've worked with this company quite a bit, and they've worked a lot at having a very controlled, repeatable immersion setup that they can repeat consistently for every different material type that they create, for every coating that they create. And they would also have done in vivo studies where they will know exactly what the relation is. So like it kind of, in terms of doing degradation experiments, it's quite beneficial to have an accelerated time frame because you can do it in a month. We do work in polymer devices as well, and the degradation time frame is 2 years. So even on an accelerated system like that, if you accelerate it 4-fold, you're still doing a 6-month experiment. So it is kind of an accelerated time frame.
But do you think then that accelerated process is kind of determining this, the pitting that you're getting versus, and it's particularly for your models, can you then change the time, the parameters in your models, and how have you even tried to do that?
It's a good question, Mika, and we haven't looked in detail at any in vivo data. I mean, obviously you have it's a physical process taking place on that surface, and that changes once you go into the body and you have, body fluid and tissue around that. I would expect that if you have a uniformly degrading device in vitro, I think it would follow that it would be reasonably uniform in vivo. But the timescale or the specific features might be a bit different. But
just the last one.
Go for it.
On that. No, and it's only because it's really interesting. I don't know anything about this. Why is it so non-uniform, the degradation of the surface, if it's a uniform material that you're starting with?
I guess it's down to the mechanism by which it degrades. Like essentially you have impurities in the magnesium and you get pits forming and you get microgalvanic cells from those impurities. So
it's down to the processing of the material.
It's down to the processing, yeah. And again, that in terms of the company we work with a lot, they want to produce high purity alloys to minimize that as much as possible. So
cool. Well done.
Any other questions?
Yes, thank you very much for this interesting presentation. I want to ask about we first make the metal to corrode and then we study the mechanical behavior of that. But what is the assumption that we are assuming that in our if we implant that the corrosion will happen I think they are simultaneous, so and they are affecting each other because of the area.
Yeah.
So what is the assumption about this point?
So we have no mechanical based corrosion mechanism in our model. I guess within a finite element implementation, it would be very reasonable to introduce like a strain based criterion to kind of have a mechanically driven corrosion process, which does happen. The big challenge with that is generating good in vitro data for it, and it's a big challenge in kind of understanding degradable materials is that if you move it into a mechanically active environment that you have cyclic loading, actively opening and closing cracks, you have a very different process to what's happening in vivo. So it is kind of the next step of kind of fully characterizing corrosion and degradation behavior as well for polymer systems. I've seen models before, say for magnesium stents. With a magnesium stent, you expand a stent open, you plastically deform it, and for those models, they have, I guess, different rates associated with the level of plastic strain. So as you plastically deform, I think you are obviously changing the inherent structure or the native structure. So yeah, big challenge.
Any questions? Yeah,
thanks very much, Ted. That was really interesting. My question is related actually to Anthony's previous one. I showed a plot earlier, a contour plot, describing for each of the specimens what the deepest pits were in 2D. And the one thing that occurred to me was that you have looked at, one specimen for 7 days, a different specimen for 21 days. Have you attempted to put one specimen in for 7 days and then measure it, then put it in for another couple of days till it gets to 21? And do you think that would differ?
We haven't looked at that. Obviously we're doing a destructive test each time, and I think actually that we found the 21-day data was actually almost as corroded as the 28 days, just due to sample variability. We haven't looked at that, but that's actually a very interesting point, because you get to see exactly how pits evolve.
The corrosion part, and then try to do corrosion fatigue or stress corrosion crack, and mechanical load and stuff.
No, it'd be interesting to look at.
There's no way you can do it in situ scanning.
In situ, I mean, you can take it out. I mean, you can take it out of the immersive.
Put it back in again.
Yeah, and put it back in. That wouldn't be too unreasonable. But you obviously wouldn't get the mechanical data. But
do you know as well, if you were to implant one of these parts into a person, is there a way of actually X-raying that person, at time periods to understand corrosion in the body? Yeah,
you would. And I mean, there's animal data there where they would do periodic CT scanning to look at kind of what the device looks like over time. A lot of the time they're focusing kind of maybe on bone formation around the device. That is there. Now, with an in vivo system, you'll never get to the same resolution to be able to look kind of at your kind of localized pits, but you could do excised specimens and put them into a micro CT scanner as well. So.
And have you noticed any correlation between pit depth and pit radius? Just out of curiosity, or is it too variable?
As in, do deep pits tend to be wide?
Yeah, or narrow. Yeah, and is there a correlation there?
I would say deeper pits do tend to be wider. It's one of the few correlations we didn't look at. we thought we'd looked at everything. I would say, and what you tend to see is you tend to see small pits forming, and then they kind of coalesce together. The schematic of that first long narrow pit, we didn't see too much of, and you could kind of see even the 28-day dog bone. It's kind of it's kind of degraded all the way around, and it's just kind of irregular, but they do tend to coalesce together.
It's very interesting.
Great,
thank you.
Thanks. Time for one more question. Okay,
Hi, thanks for a very detailed presentation. My question is on the size effects. So now you have the ASTM standard, you have a fixed dimension. Looking at the things that you measure, is one of those normalized parameters is percentage mass loss, but the rest of them is all geometric. So have you taken steps or for normalizing the geometric parameters with reference to the dimension of the specimen you use?
We have looked at specimens of in a similar order of magnitude. So I think we've maybe looked at 2 mm and 5 mm specimens. These were 3 mm specimens, and we saw same features. But you're correct in that if you go to a very small specimen, like a magnesium stent on the order of 150, 200, we haven't looked at that yet. And there are existing magnesium stents out there. They tend to corrode very, very quickly, and they have to be protected heavily by coatings. So for a small structure, a small amount of corrosion, it's going to be gone. So it is actually, it is very size dependent. But then for large structures, as you go beyond implant size, pitting corrosion probably isn't that bad until it gets really, really severe. So yeah, there is a definite size effect in what we're looking at.
So can the finite element models in the post simulations capture that?
Can they capture it? Yes. Well, I think that they certainly capture as you scale up. I think our analysis is kind of already at a resolution that would capture anything that you scale up. I think as we scale down to something that's 150 microns, in terms of a stent strut, our pit size detection had a resolution of 50 microns. So we probably wouldn't have the resolution for that, and we'd have to go to something at a higher resolution if we were scaling down. So
maybe do some crystal plasticity.
Yeah.
Yeah, very interesting. Okay, I think we've asked enough questions of Ted. Thank you very much. Very interesting talk, and lots of relevance, even though it's people working in different areas.
Yeah.
I think there's always crossover in these type of areas.
Yeah, absolutely. And I didn't get to my acknowledgement slide. I have to acknowledge the 2 PhD students, Kirsten Van Galen and Conal Quinn, who did a lot of this work over in Miotech. So they need to be thanked for that. So.
Okay, thanks again.
Thanks.